Welcome to Advanced Learning Tutoring. This is the Physics playlist. Please like this video and subscribe to our channel. The structure of an atom. Atoms are very small, having a radius of about 1 × 10⁻⁻10 meters. Atoms have a positively charged nucleus composed of both protons and neutrons surrounded by negatively charged electrons. The radius of a nucleus is less than 1/10,000th of the radius of an atom. Most of the atom's mass is concentrated in the nucleus. This is as protons and neutrons both have a relative mass of 1. The electrons are arranged at different energy levels or different shells around the nucleus. Mass number, atomic number, and isotopes. Atoms have no overall electrical charge, as in an atom the number of electrons is equal to the number of protons. The charge of electrons are -1 and the charge of a proton is +1. Therefore, the equal number of these particles and the opposite charges will cancel out. The atomic number of an element indicates the number of protons. The mass number of an element is the total number of protons and neutrons in an atom. It does not include the number of electrons, as electrons have no mass. An isotope is a different form of the same element. The atoms of the same element have the same number of protons but a different number of neutrons, and therefore a different mass number. An ion is a charged particle. Atoms turn into ions if they lose or gain electrons. To calculate relative atomic mass, you consider the percentage abundance of each isotope. Percentage abundance is how common that isotope is. An example, there are 2 isotopes of chlorine, chlorine-35 and chlorine-37. The percentage abundance of chlorine-35 is 75% and chlorine-37 is 25%. To calculate the relative atomic mass of chlorine, you multiply the mass number by the percentage abundance and you add for all other isotopes. So for chlorine, we calculate 35 × 75 plus 37 × 25. Divide this answer by 100 as our values were percentages, and we get an answer of 35.5. The development of the model of the atom. Before the discovery of the electron, atoms were thought to be tiny spheres that could not be divided. The plum pudding model. The discovery of the electron led to the plum pudding model of the atom. The plum pudding model of the atom suggested that the atom is a ball of positive charge with negative electrons embedded in it. Later, Rutherford conducted an experiment known as the gold foil experiment. The results from the alpha scattering experiment led to the conclusion that the mass of the atom was concentrated at the centre, now known as the nucleus, and that the nucleus was charged. Alpha particles were fired at a thin sheet of gold foil during this experiment. Some alpha particles were deflected, meaning they'd hit an area of like charge, and alpha particles are positively charged, but most alpha particles travelled straight through, indicating most of the atom was empty space. In the Bohr model, Niels Bohr adapted the nuclear model by suggesting that electrons orbit the nucleus at specific distances. Later, James Chadwick provided the evidence to show the existence of neutrons within the nucleus. Nuclear radiation. Some atomic nuclei are unstable. The nucleus gives out radiation as it changes to become more stable. This is a random process called radioactive decay. The nucleus gives out radiation in the form of alpha, beta, or gamma radiation. Activity, measured in becquerels, is the rate at which a source of unstable nuclei decays, whereas the count rate is the number of decays recorded each second by a detector, for example a Geiger-Müller counter. Describing the different forms of radiation. Alpha particles have the same structure as a helium nucleus. They have 2 neutrons and 2 protons, leaving alpha particles with an overall +2 charge. They travel a few centimetres in air but are absorbed or stopped by materials as thin as paper. They are highly ionising. At this stage, note that ionising is the ability of something to turn an atom into an ion, a charged particle, by either causing the losing or gaining electrons from the atom. A use of alpha particles are in smoke detectors. Beta particles are high-speed electrons ejected from the nucleus as a neutron turns into a proton. Beta particles travel a few meters in air but are stopped by materials as thick as aluminium foil. They have low ionizing power as have a -1 charge. Beta particles can be used to monitor the thickness of materials, for example paper. Gamma radiation is a wave as seen on the electromagnetic spectrum. The electromagnetic wave is emitted from the nucleus. Gamma waves travel many miles in air and are stopped by lead or meters of concrete. It is the least ionizing, as gamma waves have no mass or no charge. The use of gamma waves are used to check for leaks in pipes, medical treatments, and sterilizing materials. Unstable isotopes undergo decay to become more stable. This may be in the form of alpha or beta decay, where your unstable isotope loses either an alpha or beta particle. In gamma decay, as gamma has no mass or no charge, the isotope will not change in structure. The unstable isotope, radon-219, atomic number 86, undergoes alpha decay, losing an alpha particle of mass number 4 and proton number 2. Therefore, the mass number will decrease by 4 units and the atomic number will decrease by 2, giving us a new atomic number of 84, which will represent the element polonium, mass number 215. A radioactive form of carbon, carbon-14, atomic number 6, loses an electron when a neutron turns into a proton. Therefore, the proton number increases by 1, giving us a new atomic number of 7, which represents the element nitrogen. As electrons have no mass, the mass number does not change, giving nitrogen a mass number of 14. Half-lives and random nature of decay. Radioactive decay is random. It can often be represented by the rolling of a dice. The half-life of a radioactive isotope is the time it takes for the number of nuclei of the isotope in a sample to halve, or the time it takes for the count rate or activity from a sample containing the isotopes to fall to half of its initial level. Understanding half-life is key to being able to allocate a use to a particular isotope. For example, in medical imaging, where humans ingest an isotope for it to pass through the body to a detector, you do not want to use an isotope with a half-life of 20 years, for example, as the isotope would only decay in level of hazard by half every 20 years. So in medical imaging, you may want to use an isotope that has a half-life of a couple of hours, keeping its radioactivity level high for up to 6 hours. Radioactive contamination. Radioactive contamination is the unwanted presence of materials containing radioactive atoms on other materials. The hazard from contamination is due to the decay of the contaminating atoms. The type of radiation emitted affects the level of hazard. Example, if you get a radioactive isotope on your hand is now radioactive as you have been contaminated and you have some atoms of the radioactive material on your hand which are able to decay. Irradiation is the process of exposing an object to nuclear radiation. The irradiated object does not become radioactive. This is used in the sterilization of medical instruments. In irradiation, no physical contact is made between the isotope and the object. The object is only exposed to the surrounding area of the isotope where it is emitting the nuclear radiation. Advantages of irradiation are that sterilization can be done without high temperatures. It can be used to kill bacteria on things that would otherwise melt. The disadvantages of irradiation are that it may not kill all bacteria on an object. It can be very harmful standing in the environment where objects are being treated by irradiation and could expose people's cells to damage and mutation. Hazards and uses of radioactive emissions and background radiation. Background radiation is around us all of the time. Natural sources such as rocks and cosmic rays from space are a source of background radiation, as are man-made sources such as the fallout from nuclear weapons testing and nuclear accidents. The level of background radiation and radiation dose may be affected by occupation and/or location. Radiation dose is measured in sieverts. 1,000 millisieverts are equivalent to 1 sievert. An example question: after treatment, hospital equipment may become contaminated. Describe the level of hazard associated with contamination of technetium-99, a radioactive isotope. You should include in your answer a description of how the level of hazard changes over time. Initially, there is a high level of hazard. Level of hazard drops to a low level quickly due to a short half-life. A reminder, half-life is the time taken for the count rate to half. The shorter the half-life, the shorter and faster the isotope becomes more safe. Uses of nuclear radiation. Radioactive isotopes have a wide range of half-life values. Some isotopes may have a half-life of a few minutes, some hours, or even years. This allows radioactive isotopes to have a range of uses. Nuclear radiations are used in medicine for the exploration of internal organs or the control or destruction of unwanted tissue, as radiation exposure can kill cells. This is particularly useful in the radiotherapy in the treatment of cancers. Nuclear fission. Nuclear fission is the splitting of a large and unstable nucleus, for example uranium or plutonium. Spontaneous fission is rare. Usually, for fission to occur, the unstable nucleus must first absorb a neutron. The nucleus undergoing fission splits into two smaller nuclei, roughly equal in size, and emits 2 or 3 neutrons plus gamma rays. Energy is released by the fission reaction. All of the fission products have kinetic energy. The neutrons may go on to start a chain reaction. The chain reaction is controlled in a nuclear reactor to control the energy released. The explosion caused by a nuclear weapon is caused by an uncontrolled chain reaction. In a nuclear reactor, there are control rods. Control rods can move up or down to either absorb a neutron or let the neutron pass and collide with the next nuclei, causing your chain reaction to continue. Nuclear reactors release huge amounts of energy, which can then be harnessed and used in the generation of electricity. Nuclear fusion. Nuclear fusion is the joining of two light nuclei to form a heavier nucleus. In this process, some of the mass may be converted into the energy of radiation. Nuclear fusion occurs in the Sun, releasing huge amounts of energy. An example are when hydrogen nuclei fuse together or join to form a helium nuclei, and this process continues to form new elements.